In this video, we're going to play around with combining um, two of the filters we had looked at previously. They're just single pole first order filters. And if you remember, um, here we have a low pass shunt design. Um, just to review, um, for low frequencies, this capacitor will look like an open at the extremes. And for high frequencies, at the extremes, it'll look like a short. So I think you can see the frequency response here will be for low frequencies, they will get through this low pass filter just fine. Forgot to put my output there, but here's my low end of my frequency scale at 0 hertz. That will be an open, no problem for that. And then as frequency increases, we have that first order roll off happen. And another way you can look at that is the voltage divider view that you'd have here, where um, the output um, is across the capacitor, and the capacitor's impedance decreases as frequency increases. So as its impedance drops, it will get less and less voltage across it. So that's another way we talked about looking at that. And there is a cutoff frequency where identified where the output would drop to 0.707 of what it was here in the pass band, they would call that. So if we bring that over, here's where it dropped. And of course that's our cutoff frequency. And then we have a high pass filter. If you just look at this by itself for a minute, if the input's here, for low frequencies it's going to look like an open, as caps do, and that's going to block. So low frequencies won't get through. High frequencies, it'll look like a short at the extremes, so they'll sail right through. Again, you could look at it with the voltage divider model, and at high frequencies with very low impedance across the cap, it's going to get very little voltage across it, and all the voltage will fall across the resistor, which is also the output voltage. And at low frequencies, it'll look like infinite resistance. The resistor, as it sits in voltage divider relationship with the cap, can't compete with that, of course. All the voltage falls across an open. Lots of ways, you can say this to yourself in your head. And the result for low frequencies is all the voltage is across the cap, no voltage across your output. So if we draw that frequency response, we said high frequencies, here at the high end of the scale, are fine. The cap looks like a short at very high, but definitely very low impedance here. And then as frequency decreases, that's where our output voltage is going to decrease, because the cap starts to look more and more like an open. So let's draw that in, and we'll see. We'll pick the same cutoff frequency, and that would occur if we have the same values for these caps and for these resistors. And for this exercise, I think we'll just keep the same values that we used previously. It gives us an easy way to compare things. I think it was a 10K resistor, right? And 0.01 microfarads for the cap sizes. So what we're going to do is make the input signal here run through both filters. And that's known as cascading. So we're going to cascade the low pass filter with the high pass filter. Basically, just putting them right in line with each other, putting them right in series. You could kind of describe it that way as far as the signal sees it. And now we're going to have a different type of frequency response. I mean, the signal at the input, well, if it's too low, it's going to have trouble with this high pass portion. It'll have trouble getting through there. And so if it's too high, it'll have trouble getting through this portion of the circuit. And we'll see what the frequency response winds up being. It's going to be what's called a bandpass. The only frequencies that get through are going to be frequencies that can make it through both filters, right? So it's going to be in here. In other words, it's a sort of it's an and function, really, anytime you put something in series. And that's exactly what we're doing. We're anding a low pass and a high pass. In other words, the input signal has to get through the low pass and the high pass. Whatever frequencies can do that will make it to the output. And here they are. It's going to be right in here. From here to here, they've got a chance. Anything below that can't make it through the high pass. Anything above that can't make it through the low pass. So we'll look at that frequency response and sort of some calculations in a minute. I want to say something about cascading. Here we just literally just put them right together, and there's a reason we did that, but that would be the simplest possible way to cascade filters. Oftentimes, and you'll see in chapter 23, you would buffer the cascading. So in other words, you would run a low pass pole to an op amp, which would buffer the output. And so you would have an active low pass cascaded to an active high pass. In other words, you'd have an op amp sitting right in here to buffer. Because without the op amp, it is true that this high pass winds up putting a load on the filter. So this impedance is in parallel with C1. So it's true that you want to think in terms of oftentimes cascading with active filters. Maybe is something, but like I said, we'll get to it. You'll see why I did it this way. Well, it's very simple, and it's a nice simple thing to look at, but it also leads us into a classic circuit that I want us to do for this exercise. So, but it's called cascading, and we literally did it without any buffering. Just put them right together. Also, while I'm painting the backdrop for this exercise and digressing a bit, I wanted to mention again that as we said, well, it will be a bandpass response, and we'll define that in a minute. But I wanted to emphasize that this is just a way to make a bandpass response. We've said it before, I think, that when it comes to filters, there's so many ways to create one, and I wanted to remind you that inductors, we haven't brought them into the mix, but you can do filter networks that use inductors, capacitors, resistors. Oftentimes you leave inductors out of the equation. They aren't as ideal. They have that winding resistance. They're heavy, they're bulky, take up space. But there are times where they come into the mix. So I did just want to give that broad perspective again, that this circuit we're going to do will be a bandpass response, but it's not the way that you make a bandpass filter. It's a way, and probably the simplest way, which is a good place to start. But from there, you can buy a book, that's 300 pages of active filter circuits, or just filter circuits in general that people have cooked up over the years. So lots of ways to do it. We'll take the simplest way, and it'll lead us right into a classic circuit. So what is a bandpass response? Well, we said there's a band of frequencies right in here, right? That will have a chance of getting through this cascaded low pass and high pass. So it is a bandpass response. Now, let me draw another chart, and we'll show you what that's going to look like. So here is the plot of what the frequency response would look like for this cascaded low pass and high pass. I tried to keep it a little bit to scale. The output here will have one frequency, and exactly one, that is maximum. It looks a little flatter at the top than I wanted it to be, but that's okay. This is going to be known as your center frequency, and it is the frequency that will have the highest amplitude, And you might make a guess and you'd be right. If you remember the cutoff frequency, you could calculate with a simple um, formula. 1 over 2 pi RC gave you the cutoff frequency for the low pass. And if you use the same component values, then you'll have the same cutoff frequency. It's also 1 over 2 pi RC for the high pass. So, and that point, you can probably see intuitively that is the frequency that's going to be getting through the easiest. It will be this point right here, your center frequency. So maybe not surprisingly, F sub O, the center frequency for a bandpass filter, is still 2 pi RC. Well, for this bandpass filter, because we've kept things very simple. We have made the component values identical for the low pass and high pass. That's why it is this easy as far as center frequency. In other circuits, you might have active filters where they're they're buffered, so you don't have to suffer such loss. I mean, I try to do it to scale. When you get through both of those cascaded with no buffering and no gain with the, that you could get from an op amp, yeah, your output does come out pretty low, and I'll show you exactly where that point is in a minute. But speaking of a more versatile way to put together a low pass and a high pass, you use an op amp. You can add gain to it. You can vary. You can have different values for components, and you can then you'd have to use a different formula. It wouldn't be just as simple as 1 over 2 pi RC. In fact, it's going to be the geometric center of the two cutoff frequencies. So that it would be this cutoff frequency times this cutoff frequency square rooted would give you the center frequency. Chapter 23 lays that out nicely. So I just wanted to say, my point there isn't that you remember that little blip I just said as much as you remember that 1 over 2 pi RC is not a universal formula for center frequency for bandpass. It only happens in this case. So another thing specific to this example is the level of that center frequency is actually going to be very attenuated. It'll be 1/3 of whatever you put at the input. If you set the frequency for the center frequency, and let's say you just put 1 volt in, maybe we could use that. We could normalize to 1. So let's say you had a 1 volt input, and you're up here. And this is the attenuation that you'll see from this cascaded low pass, high pass filter network. The most you'll get out is if you set it for your center frequency, and if you want to, you can put that in here. I think it was 1.59 kilohertz. I'll check that. If I'm wrong, fix that. But yeah. So let me see if that. Can you see that? I'm just gonna move this out of the way. Might have written that off screen. So let's put that here maybe. Okay, so I think it's 1.59 kilohertz. So if you put 1.59 kilohertz at the input and a 1 volt peak, perhaps, then you'll see a sine wave. Again, you won't see this kind of a plot, remember, but you'll see a sine wave, a 1.59 kilohertz sine wave, but the amplitude of that sine wave will be 1/3 of what it was at the input. It'll be 1/3 at the output of what it was at the input. That's what I'm trying to say. So this is a bandpass response, and something that all bandpass filters are identified with is a couple of traits that we will want to get maybe those introduced. So we already looked at center frequency. So all bandpass filters have a center frequency, but then they also have what are known as side frequencies, and the side frequencies are um, there's two of them on either side of the center frequency. For example, as you start to get lower, it starts to roll off and attenuate. And when you get to 0.707, below the pass band level. So we're not talking 0.707 of the input. We're talking, in this case, I mean, again, it could be that if you had buffering and things like that. But for our simple example, this is what we want to identify as our cutoff frequency number one would be there. And again, where it drops to 0.707 as you increase the frequency would be the other cutoff frequency. Sometimes people refer to them as the side frequencies. So again, good to introduce this stuff. This is all uniform to any bandpass filter. It will have a center frequency and two side frequencies, a lower cutoff and another upper cutoff frequency. And again, those you would identify once you know the amplitude at the center frequency. Then you would identify your side frequencies by the frequency that causes the amplitude to drop to 0.707 of what it was at the center frequency. So I wrote in some numbers. I mean, if we normalize to 1, or in fact, if we literally put in 1 volt for our input to this cascaded filter network, 1 volt on the input, we would expect at 1.59 kilohertz to see a peak amplitude. If we had 1 volt peak on the input, we would expect to see a peak amplitude at the output at 1.59 kilohertz of a sine wave. We would expect to see that peak voltage be 0.333. And if we go searching for our side frequencies, you would just have to vary the frequency of your input signal, take it lower until the peak voltage of the sine wave drops to 0.235 and stop at that point, and that is your lower cutoff frequency identified. And then spin the frequency back up, go above 1.59 kilohertz, and keep increasing the frequency until your output peak amplitude drops to 0.235, and you'll have identified the upper cutoff frequency. Here I've listed some of the universal parameters for a bandpass filter. We'll get to this in a minute, but we stopped at bandwidth here. Once you identify the side frequencies, the bandwidth is the range that sits between the two cutoff frequencies. So it's the distance from FC1 to FC2. So bandwidth is just FC2 minus FC1, just that simple. Q for a filter is an indication of how narrow the bandpass is, with some perspective on where you are in terms of frequency. So it's you know, that narrowness is very relative to where you are in the frequency range. For example, we're sitting for a center frequency, we're sitting here at 1.59 kilohertz. Let's just throw some numbers in here. If we had a bandwidth of 200 hertz, for example, so I mean, you'd have 100, maybe, well, it wouldn't be 100 in each direction, so I'm trying to do this quickly, but let's say we have a bandwidth of 200 hertz, and it wouldn't be 100 in each direction because it's the geometric center here that we'll try to define that too quickly. I don't want to get too bogged down. I mean, chapter 23 lays it out for you nicely, and if I try to do it too briefly, it might just be annoyingly confusing. But if you're at 1.59 kilohertz and you have like a 200 hertz bandwidth, I mean, I think you can see you're up here in the 1,000 range and you're here at like the 200 range, that's a pretty high Q. That's a pretty narrow um, uh, frequency selection, um, because you're in this sort of realm and you have this. But in contrast, picture a bandwidth of 200 hertz, but you're down at a lower frequency. So I mean, I don't know, a bandwidth of 200 is not going to be very selective if you're sitting down here at we could just say 100 hertz is your center frequency. I think you can see um, that seems like a very wide filter, doesn't it? It'll let everything from 100 hertz down to zero and 100 hertz up to 200 hertz. Um, again, I centered it. I didn't mean to center it algebraically like on a number line. So it's logarithmic center, but I'm going too fast, but I know. But the thing I'm trying to point out is what this Q is. It's just trying to show perspective on what your bandwidth looks like, um, but you can't just use bandwidth to identify how narrow. It's how wide is the bandwidth, and that's a certain range of frequencies. But how high? Where are you working? In what area of the frequency spectrum? You know, how high, how low. So okay, I'll get off that. I think we've used the money example before. You know, uh, if you have $100 and you have a change of $200, that's very significant. If you have $1 million, and then you have a $200, you know, change in either side of that, uh, not as significant. So that'd be very narrow. The $200 is very narrow compared to millions. So it'd be maybe another thing that helps with that. All right, and one more thing, just to bog us down. I mean, I don't want to bog us down. I know I am, but it's because I'm trying to introduce sort of this example and at the same time use it as a way to introduce you to um, bandpass filters in general. So that's what I'm juggling here. Um, for our example, well, this holds true for any bandpass filter. This does, and this does. Those are generic, and we can apply them. We had said for this network, you know, our center frequency is just this 1/2 pi RC, but that's because of our simplistic nature there of the circuit. The generic one for finding center frequency, it's going to be the product of the two side frequencies square rooted. That's going to put you right in the middle of this if this is a logarithmic scale. So, you know, if this is 100 hertz, um, and this would be 10 kilohertz, you'd be right here at 1 kilohertz for your center frequency. So I wanted to throw that out there, that the more generic one that applies to all bandpass filters. And while I'm bogging us down, I'll just do one more thing. All the way back to what we said, where we'd probably be cascading active filters, where you have op amps sitting in here to act as a buffer so that this high pass doesn't crash in on this voltage divider and change things. Um, so you'll see it in chapter 23, but if you do that approach, you're probably not going to pick the same cutoff frequency for the low pass and the high pass. You want there to be overlap, so you would do something more like, you know, your high pass might come in like this, and your low pass might come in like this, and you're going to have side frequencies that come from 1/2 pi RC, but they're different. Uh, they're going to be a side frequency and a side frequency, um, and then you find your center frequency by taking two side frequencies, which do each come from 1/2 pi RC. If you're doing a single pole um, uh, design like these, but you might not use the same component values. And what that does is that gives you some overlap, a little more overlap for your filter. I mean, you can see here uh, as I have sort of all this area now to work with, instead of just a little bit of one frequency that they had in common. So, um, okay, so now that I've totally messed up that drawing, but like I said, my intent is to sort of use this as an introduction to bandpass filters in general as well. So that's why we kind of went through all that. For this specific bandpass circuit, there is something I want you to keep in mind for future reference, because we'll need to refer back to it. Maybe two things, in fact. And they are that we're going to have one frequency, the center frequency, that gets through with the highest amplitude. But I need you to remember, even at its best, at the highest amplitude, we're going to be down 1/3. So what that's telling us is we have an attenuation factor here for even the frequency that gets through the easiest. For this network, the attenuation, we're down 1/3. So you got to remember that. We're gonna refer back to that later. The other thing about the center frequency is it's the only frequency where there's no phase shift from input to output. So the phase angle input to output is 0 degrees at this center frequency. Those two things are really important. We're gonna use this this network for future exercises too. So keep that in mind. So at that center frequency, we'll be down 1/3 comparing the output to the input, but there'll be no phase shift. The output will be in phase with the input. In the lab exercise where we actually build this network, again, these are the easy identifiers for the center frequency. At the bench, you just vary the frequency until you see the output come in phase with the input, and also that'll also be the frequency where the output is the highest it can be, albeit 1/3. So don't think you're going to match the input, but you're going to get the highest amplitude you can, which will be 1/3 of the input, and you're going to at the output, and you're going to get the input and output in phase. That's an easy way to identify center frequency. So at the bench, you can do that with your scope. In the theory setting, well, for our circuit, it's this 1/2 pi RC, or for a more generic approach, if you have cutoff frequencies that you're cascading that are different than each other, then you're looking for a geometric center of those cutoff frequencies, square root of the product. And here's kind of a punchline for this whole presentation. Take that capacitor, move it over to here. That's what I've done in this drawing. So take a minute to see that that's in fact what occurred. This is now a classic circuit known as the Wien Network, from which you get maybe a Wien Bridge oscillator that we'll look at down the road, which is actually what put Hewlett-Packard on the map. They found a way to use a Wien Bridge network to create a Wien Bridge oscillator, and then he did one cool little trick with a simple lamp, like we used in the first week of school. And they used a simple incandescent lamp and the fact that its resistance goes up as current goes up, and they used that in a feedback network with the Wien Bridge feedback oscillator. Long story short, that was their first product. It was the lowest distortion sine wave oscillator on the market, put Hewlett-Packard on the map, got them on the road to the big worldwide company they are today. So the Wien Bridge oscillator is a classic circuit. The Wien Network, as we see here, is a classic, or as I like to call it, the world's coolest voltage divider. You know, it still has the same traits. Well, and that's the thing that fascinates me, and maybe I shouldn't as much as it does. I don't know. some thoughts I always have is, since when can you move something like that in a circuit and have it stay the same? In other words, what I'm telling you is this whole presentation, it doesn't matter which of these arrangements you use. They both behave identically in terms of all this stuff. And there might be some other attribute that might be different. But as far as the bandpass function, the center frequency, um, and things that are true about our bandpass circuit that we talked about, it's all true for the Wien network, which is more the classic circuit that you do see. And you'll run into this, and I'm sort of doing it backwards. I did this presentation to sort of lead up to the Wien network in a way that gives you insight, I think, into the Wien network. It is, you know, parts of it make you think exactly low pass, high pass put together. However, not so much cascaded like we did here, kind of superimposed, you might say, right? I mean, it looks like we kind of just laid a low pass on top of a high pass. And so some of those things you could spend time looking at. I mean, lots of people do, and it's a fascinating little network, I think. I mean, the zoomed out look at it, of course, isn't so hard. I mean, if you see the caps are still doing what caps do, I mean, uh, I think you can see the bandpass nature of it show up the same way we saw over here. I mean, look at your capacitor here that will block, you know, low frequencies and pass high frequencies. So you have your high pass component still, and in fact, you're going to, um, you know, it'll be a series design high pass. And here you've got your shunt design that'll shunt high frequencies, so low frequencies will get through. Or maybe another way of maybe looking at that is just pick low range of the frequency and see what happens. So low range of the frequencies, caps look like opens. Okay, and high range of the frequency, and so the open here, and you're not going to get any voltage on the output. This will claim all of it. I mean, what happens with the Wien network? You still have why I call it the world's coolest voltage divider. Uh, it is this impedance of the parallel resistor and cap that are going to claim a certain amount of the input voltage as it sits in a voltage divider series relationship with the other components. Yeah, so you're going to have sort of that thing going on. So yeah, low frequencies, this gets all the voltage drop, and there's nothing for the output. And at high frequencies, you've pretty much shorted your output. This looks like a short, and you get 0 volts across your output for that reason. So there is still this, like we said over here, I guess the shunt design low pass and the series design high pass, and there's those elements are still in there. But it's an interesting little circuit to look at for sure, and try to figure it out. You can do analysis on it. You have to go back in our book and look. We skipped over the series. I mean the parallel analysis of impedance. But if you look at that, you'd have to create a series equivalent here, and you'd start filling up some pages with pencil and paper, to do the calculations. But yeah, it's an interesting circuit. I think it's cool that you can look at the Wien network and sort of think of it in terms of a cascaded low pass and high pass, but it really isn't. I mean, this is truly cascaded low pass, high pass, and this really is a different layout. It's a different circuit. It is, and they behave the same. That's the fascinating part, I think, and you'll see that. So when it comes to the lab exercise, I will probably have you build this and get it up on your scope, and then if you make it on your breadboard neat enough that you can have easy access to C1 here, and you can just pluck that capacitor out and move it over to here, and you now have a different circuit. It's the Wien network now, and nothing will change on your scope. Everything will look the same. It'll function the same. One sidebar: when you look at drawings of the Wien network or Wien Bridge network that's being used for something, a lot of times they'll pair R1, C1. They'll pair these two components, and they'll pair the two parallel components, R2 and C2. Um, you know, I it kind of breaks up this kind of understanding that we developed when we looked at it as low pass and high pass cascading. So um, I'm not sure if there's a reason to do it that you see it grouped like this for theory reasons, or if it's just the layout, of the schematic symbols that maybe causes it to be labeled this way. But it's very typically drawn with these two associated and these two associated, and but I mean, I think you can see for jumping back to the cascaded one. I mean, R1 is and C1. This would have been C1 for us. So these two would have been more doing something, and these two. But again, that's a little bit of a gray area for me. I always just think that's in my head. I'm sort of always kind of wondering about that and pondering it. I've even seen, like, well, and in our textbook, they'll start explaining the Wien network as R1 and C1 being a pole, and R2 and C2 acting like a pole. I don't know about that. Maybe I'm missing something, but sometimes I read that with a grain of salt, like in our textbook, and it's in a lot of places I've read that, where when they try to go backwards, they'll just show you the classic Wien network circuit, and they'll explain it as here, this acts like a high pass and this acts like a low pass. And I'm thinking, I don't know. I mean, I'm not saying I'm right for sure, but you know, here's sort of where I see a low pass, and here I see a high. Whatever. I mean, but that's a sidebar. And again, I might be missing something. But with this introduction, you know, I don't know. Maybe I've introduced you, hopefully, to the fascination of this little network. It's, like I said, it's a very classic circuit, and it's one to ponder, and it's one to look at, and one to keep looking at, and maybe you'll be curious, and maybe you'll send me an email someday that completely smooths out, maybe disassociation. But don't worry about it too much. But I mean, like I said, for me at this point in my sort of thinking, I sort of, I sort of go, okay, call them whatever you want, and I'm not saying I have solid footing either to know exactly why you might pair them up. But yeah, so it might just be schematic location. So this video kind of got too long. I knew it would. I suspected it would. I hope I didn't bog it down too much. If you need to review it, go back and pick out the highlights. This is where I was driving. This association, I think is fascinating, and maybe you do too. I don't know. Or maybe you're just worn out at this point. But yeah, we get there. We can build either one. We can look at it with our scope, and also I hope for the Bandpass in general, it served as an introduction. Look in chapter 23 if that was totally confusing the way I went through that very quickly, the generic Bandpass versus our specific build. But you can use chapter 3 to maybe sort that out. So we'll wrap it up here because I see it's getting really long. Cool association, Wien Network, the world's coolest voltage divider, the Zen Bandpass.